Welcome everyone to the third episode of this short video series called The Mathematics of Music. Last episode we discussed about how Pythagoras discovered the importance of ratios in music, and then I established that sounds are a complex combination of multiple frequencies that we call harmonics. Also, I scarcely talked about the Pythagorean tuning, which can be obtained by stacking 3:2 ratios on top of each other. However, the tuning we use today is quite more complicated. Hence, today we will talk about modern tuning systems. What is an octave? Well, last time I defined an octave as a 2:1 ratio between the frequencies of two sounds. Also, note that this concept is covered in the glossary that can be found in my support document. Now, let's look at a piano. The regular grand piano has 88 keys spanning 7 octaves. That means that if you take the lowest note on the piano, you can multiply its frequency 7 times by the number 2, and the frequency will still be on the piano. My keyboard, on the other hand, spans 6 octaves. Now, how do you think we obtain the notes in between one octave? Well, we split the octave evenly. It's that simple. In other words, each octave is divided evenly, 12 times. First, to elucidate this explanation, we need to label each note. In English, we label notes with the first letters of the alphabet. Let's start here. This note is A. This note is B, C, D, E, F, G. A, B, C, D, E, F, G, and you get the idea. Note that the octaves get the same label since they sound like they are the same note. Now, the black keys in between the white keys can be labeled two different ways. Take this one for instance. It's in between the notes A and B. Thus, we can either call it A sharp, sharp meaning higher, or B flat, flat meaning lower. So you can either call this note A sharp or B flat. The next black key is in between C and D. Thus, we can either call it C sharp or D flat. Now, you know how we label notes in music. So, how do you determine the frequency of each note within one octave? Well, we need to refresh our memories in some elementary mathematics. If you multiply the number 2 by itself 3 times, so 2 times 2 times 2 times 2, you will get 2 to the 4th power, since you multiply the same number 4 times. Now, if you multiply the number 2 to the 4th power by itself, so 2 to the 4th power times 2 to the 4th power, you get 2 to the 8th power. Thus, when you multiply a number by another and they both have exponents, you can add up the exponents. This rule is fundamental to equal temperament. An octave is comprised of 12 notes: A sharp, B, C, C sharp, etc. This is the equation that allows us to find each frequency. I'd like to focus on the unusual 12th square root of 2. What does it mean? Well, the 12th square root of 2 is simply a sophisticated way to talk about 2 with an exponent of 1/12. Now, I said that when we multiply a number with an exponent with another, the exponents add up. Thus, if I multiply the number 2 to the 1/12th power by itself 12 times, we will get 2 to the 12 over 12. And if we simplify, we notice that 12 over 12 is just 1. So this is just 2 to the 1st power, which is equal to the number 2. Therefore, each note corresponds to a multiplication of 2 to the 1/12. But don't worry, this seems rather complicated, but I will demonstrate with a piano. This is the note A. To get the frequency of the note A sharp, we need to multiply this frequency by 2 to the power 1/12. This is the note B. To get the frequency of the note B, we multiply the frequency of A by 2 to the power 1/12 2 times. Thus, when we get to the octave, we will have multiplied the number 2 to the power 1/12 12 times, which corresponds to exactly double the frequency. This respects the definition of the octave I previously provided. With this explanation, the formula should now be easier to grasp. If you want to find the frequency f of any note, you need to multiply the initial frequency by the 12th square root of 2 n times. N is the distance between two notes. For example, if I want to know the frequency of the note A sharp, knowing that A is equal to 440 Hz, I multiply the frequency of A one time, since I only had to go up one note to get to A sharp, therefore n is equal to 1, and we multiply by the 12th square root of 2. This gives me 466 Hz on my calculator. However, last time I mentioned that our brain prefers simple ratios. We can all agree that a ratio of 2 to the 7/12th power between two notes is far from simple. Yet, it sounds like this. To my ears, at least, this is not dissonant, meaning that it's not unpleasing. Now, if you take a calculator and compute 2 to the 7/12th power, you will get 1.498307. This is very close to the simple ratio 3/2, which is equal to 1.5. Also, the ratio of 2 to the 5/12th power sounds like this. On the calculator, you see that it's equal to 1.3348. This is very close to a 4/3 ratio, which is equal to 1.333. Hence, the two main reasons why equal temperament is used today are the following. First, it sounds pleasing to the ear. Equal temperament sounds rather pleasing since it roughly approximates some simple mathematical ratios, like 1.498 instead of 1.5. Like Pythagoras discovered, this is something that our brains truly enjoy, even if the ratios aren't perfect. Secondly, it's symmetrical. To get all the notes within one octave, I took the note A and then I multiplied the frequency by 2 to the 1/12th power several times. The thing is, I wasn't obligated to begin with the note A. In fact, I can apply the same process starting on any note, like C for example. So if I have the frequency of the note C, I can easily find all other notes. This is relevant because in music we like to have centers. This is what we call tonality, since we have a tone that is central to the piece. Thereafter, we choose melodies that are relative to this note. Sometimes, however, particularly in jazz, we like to modulate our tonality, meaning that we change the central note. Here is one excerpt that might help you to fathom what a change of tonality sounds like. Ain't no mountain high enough, ain't no valley low enough. Don't you know that ain't no mountain high enough, ain't no valley low enough. As you can see, a modulation is a tool in music that you use to shift the whole song around a new center, and this often gives energy to the music since the listener grew accustomed to the first tonality. Now, since equal temperament is symmetrical, we have no problems whatsoever doing modulations, which is typically not the case with other tuning systems. We've now covered the basis of equal temperament. Now let's talk about another important tuning system, just intonation. Just in case you forgot, last episode we talked about the harmonic series. This is something that occurs in nature, and it allows us to distinguish the sound of a piano from the sound of a guitar. They sound like this on the charango. Just intonation is a system that utilizes the ratios from that phenomenon. Let's say I'm looking at the harmonic series from the note A, which is equal to 220 Hz. According to the equation I showed last episode, I should get the frequencies 440 Hz, 660 Hz, 880 Hz, and so on. Now let's look at the ratios between the frequency of each harmonic. Between 220 Hz and 440 Hz, we have a 2:1 ratio, the octave. Between 660 Hz and 440 Hz, we have a 3:2 ratio. Between 880 Hz and 660 Hz, we have a 4:3 ratio. If we make a diagram out of the most pleasing ratios we get from the harmonic series, it looks a little bit like this. Most musicians will tell you that this tuning system sounds more pleasing than equal temperament. This is why some musicians say that the piano is intrinsically out of tune. However, if I want to modulate a song, and by that I mean if I want to use the tonality of D instead of C in the middle of my song, I need to use a different piano. Thus, all 12 notes in between one octave would each require their own instrument so that the notes are tuned properly. This is a huge inconvenience, which is why just intonation isn't the tuning standard, although it used to be. In this episode, we've covered more complicated subjects than those from the last episodes. But now we know how music notes are labeled. We also know how equal temperament uses exponents to find the frequency of each note. Furthermore, we talked a little bit about just intonation, which is a tuning system that utilizes the ratios from the harmonic series. That being said, I argue that just intonation can be integrated within songs that use equal temperament, and it has already been done before, but there hasn't been enough discussion on this topic in my humble opinion. In the next episode, however, I will show you how this can be achieved. Thank you all for listening, and I hope to see you next time.